In this lesson, I want to briefly review what ionic bonds are, kind of how they form, and then importantly some properties of ionic compounds, including the lattice. First of all, an ionic bond is a bond that's formed when electrons transfer from one atom to the other. The result of that transfer is the formation of ions. And in an ionic bond, you always have two ions. You have the positive cation and the negative anion. Those two ions, when they form, are attracted to each other through the electromagnetic force, which is similar, it's analogous to the gravitational attraction, for example, between the moon and the earth. And we are well aware that the moon and the earth never actually touch. They're just simply attracted to each other over a distance. And we see the same thing in ionic bonding. The cation and the anion never actually touch each other. Ionic bonds are typically formed with a nonmetal serving as the anion, and sometimes a metalloid. And then usually, almost always, the cation is a metal. So in high school chemistry, we get away with overgeneralizing and saying that ionic compounds always have metals, have one metal in them. Here are some very important properties of an ionic compound. Please make sure you remember these. Number one, compounds form a lattice. Now, on the next slide, I'll show you a picture of a lattice, but just for now, lattice is a regular repeating pattern. For those of you who may have a mom or a dad or a grandparent who gardens, you may see them planting vines that grow up on a lattice. It's a regular checkerboard kind of an arrangement, just a regular pattern that the person who makes it uses. The formation of an ionic lattice is an exothermic process. In other words, we get energy back when the ionic compound forms. It would be kind of like bringing two magnets together. When they slam together, there is a release of energy because they are together now at a lower energy state than they were when they were being held apart. They want to come together, but they were being held apart. It takes energy to hold things apart. So when a cation and an anion come together, they are going toward a lower energy, more stable state, and they're going to give us back that energy we were using to hold them apart. Ionic compounds are very hard. If you've ever touched or tried to crush a few grains of salt in your hand, you realize they're pretty hard. But ionic compounds are still brittle. And the reason they're brittle is because when the lattice forms, the bonds, the attractions between the cation and the anion is very rigid. There's not a lot of room for movement. So when you strike it with enough force to get them kind of out of line, the bond can be severed. Ionic compounds have very high melting and boiling points. That is due to the strength of the ionic bond. To melt or boil an ionic compound, what you're going to have to do is separate the ions from each other. Well, if they're really attracted to each other, it's going to take a lot of energy to overcome that attraction. Ionic compounds do not conduct because in the lattice, they are locked into place. By they, I mean the electrons. To be conductors, you have to have electrons that are free to move around and take the energy with them. Well, if they're locked in a lattice, they're not going to be able to do that. Now, ionic compounds will become electrolytes if you dissolve them in water, and by dissolving ionic compounds in water, you are overcoming the lattice through all the ion dipole forces between the water and the ionic compound, but they separate. And when they separate, the ions will allow current to travel, but not in the solid form. So here's that picture of the lattice I was alluding to. This is the one for sodium chloride, salt, table salt. Notice in the lattice you have these anions, and they're always going to be surrounded by, immediately adjacent by, a cation. And that cation is going to be surrounded by not only the original anion, but another nearby. So it forms this almost never-ending network, this pattern of positive, negative, positive, negative. And they're different shapes. This particular one forms the shape of a cube. A lot of them form the shape of a cube. This one in particular is a simple qubit structure where there's an ion at the corner of the cube, at every corner. We talked before when we did mole conversions about formula units. So let me show you here now that we're looking at a lattice what a formula unit looks like. Out of all of these ions here, you look for the simplest ratio. So for example, there's a 1 to 1, and that repeats itself, 1 to 1, 1 to 1. So out of all this, we can simplify it down to the simplest repeating structure here as being 1 anion for every 1 cation. So the formula unit for NaCl is NaCl, just 1 sodium and 1 chloride ion. So as I use my cursor here, I'm drawing an imaginary circle around the formula unit for sodium chloride. And that formula unit, again, just repeats itself over and over and over. And let's discuss now how lithium forms an ion. So I just picked a random element. Lithium has 3 electrons arranged in its electron cloud. You have the inner core and the valence shell. And then there are 3 protons in the nucleus along with 3 neutrons. Lithium, of its 3 electrons, only 1 is valence. I'm pointing to it here on the screen. The inner core, which is the first energy level, is full. So only that 1 valence electron wants to do anything. The octet rule tells us that atoms want to have 8 electrons in its energy shell, its outer energy shell. So for lithium, that outer shell can hold 7 more. Potentially, it could gain 7 more. But that's not going to happen. It is going to be much easier for lithium to lose that 1 electron, and then that inner core that we talked about, well, the 2 electrons, will become the outer level. And that's easier to do than gaining 7. So that outer core, or so that outer ring goes away now as the electron is lost. That leaves lithium now with only 2 electrons, and the inner core now becomes the valence shell. But lithium is a +1 ion at this point. The lithium atom is not inherently stable. Electrons don't just go flying off on their own. They have to be teased away. They have to have their ionization energy conquered, if you will. So lithium needs help. So a more electronegative element is going to supply that help. And fluorine is an example of an element that can do that. So fluorine is a little bigger atom. It has a full first energy level, and then it also has now 7 valence electrons. So if fluorine really wants 1 more electron, and then lithium has 1 to offer. With a low ionization energy, lithium easily gives up or has it taken, however you want to think about it. Fluorine takes that electron from lithium and becomes the fluoride ion. That action is fairly separate from the bond formation. As of right this moment, there is no bond formed between these 2 elements. Now, the transfer has taken place. You now have a positive lithium ion and you have a negative fluoride ion. Now, they're going to be attracted to each other. And they're going to come together. They're going to come closer. They'll come close, and where they stop depends on where the nuclei of each atom, or each ion in this case, repels. So you're having a pulling together between positive and negative attraction, and a pushing apart by positive-positive repulsion between the 2 nuclei of these ions. And they will stop at the point where those 2 roughly cancel each other out. Again, ionic bonds never touch. They just come closer together. So this becomes the LiF, or lithium fluoride ionic compound. And that's how we make ionic bonds. Sometimes more than one electron is exchanged, sometimes a lot, sometimes 3 or 4, but mostly 1 or 2 for most ionic bonds. All right, let me know if you have any questions.